So today we're going to look at sort of how limits connect to the main idea of calculus of derivatives and look at the definition of the derivative. So the definition of a derivative, sometimes called Newton's quotient, is just the same or very similar to Formula 2 that we saw. The main difference is that generally we don't just plug in a certain value, we plug in a variable for x to figure this out as an equation. So f prime of a is the limit of any number as h goes to 0, and remember that a limit is something that you get really, really close to. So the derivative, what it finds is it finds the slope of a tangent line, that instantaneous rate of change at each point on the function. So when we plug in just a variable, what the derivative gives us is a slope function, an equation of all the slopes of all the tangents, no matter where they are. Now we've looked at this alternative way, this was formula number 1, of writing the derivative. And the derivative itself is a function. We call it a gradient function or slope function of all of those slopes put together. Some notations. The first two, well, all three are quite common. F prime of x, we'd use that if your original question had f of x had function notation, then it would make sense to keep the function notation. Y prime, you'd use that if your original equation was y equals, then that's one way to write the derivative. And Leibniz notation, dy dx, also if you have y notation. But you can use all three of them interchangeably. So some strategies for finding the derivative using the definition. Okay, we're going to use our algebra skills just like we've developed in all of our limits all the way along. So we're going to plug in the function into the definition with the x plus h plugged in. We're going to expand and simplify like terms until you can factor out that value of h, because remember, with a limit, you want to cancel out that thing on the bottom that's making you divide by 0. So if we're using the definition with the h on the bottom, you're dividing by 0, and you want to factor that out so that that goes away. So what does this all look like? Well, we'll get to some examples in a bit. Once you are no longer dividing by 0, that h has been canceled out, then you can plug in your limit and evaluate it to find out what it's equal to. Right? And a note that with square roots, we sometimes use the conjugate, and we've done that already with dealing with limits. So the difference in these questions right now, as opposed to the questions that we did the other day, is the other day it was asking you to find a slope at a specific point and then finding that equation of that tangent at that specific point. Now what we're doing is we're using the definition to find the actual slope function, to find every single slope that could exist. So according to our steps, it says, first of all, plug in your function into your definition. So our definition, f prime of x, I'll just use one notation, limit as h goes to 0, we'd have h on the bottom. Instead of f of x plus h, if I plug that into my function that I'd have, it would be x plus h squared. And instead of f of x, well, in my example, f of x is x squared. I would just plug that in. So step 1 is plugging the actual equation into the definition using what you know about function notation. Step 2, now we're going to use our algebra skills to expand, simplify, and our goal is to get rid of that h on the bottom that's causing this limit to be a problem. So I can expand. I have to rewrite the limit as h goes to 0 until I get rid of that h. So I can expand this x squared plus 2xh plus h squared minus x squared. Might notice that your x squared simplify. And then with what is left on top, we have a common factor of h. So I can factor that value out, which was our goal, to simplify that h on the bottom. Once that h is simplified on the bottom, now you can legitimately plug in 0 for h. You're no longer dividing by 0. And if you plug in 0 for h, you just get 2x. So our derivative is equal to 2x. Now, what I'm going to do next, instead of moving along with the examples, is just sort of do a review. Oh, I'll do part B for this one first. Part B says, find f prime of 3 and describe the meaning of f prime of 3. So in A, we found out that f prime of x was equal to 2x. So f prime of 3 is equal to 2 times 3, which is 6. Describe the meaning of f prime of 3. F prime of 3 equals 6 means that the slope of the tangent at x equals 3 on f of x equals x squared, because that was our original function, is equal to 6. If I would draw a picture of my original parabola, I have the point 3, 9. If I drew a tangent at that point, the slope of that tangent line is equal to 6. So what the derivative does, when you find the derivative function in general, is it creates an equation to calculate any slope anywhere. We could figure out the slope was 6 at 3, 9 just by plugging in 3 into the equation. Okay? If you wanted to find another slope, if you wanted to find the slope at -2, 4, you could plug -2 into your derivative function, and 2 times -2 would be -4. I would know the slope of that line is -4. So the power of the definition of the derivative is we find an equation that works for any slope. So let's look at how we've gotten to this point, what we led up to. And we're going to use x squared and 3, 9 as our example. Okay? So f of x equals x squared at the point 3, 9. The first thing we did, we had formula number 1 for slopes, saying the slope was equal to the limit as x approached a of f of x minus f of a over x minus a. So what is our x value approaching? Our x value, in our example, when we wanted to find it at 3, 9, our x value was approaching 3. If we did that, we would have f of x, which is x squared, minus f of a, plug in 3 into this, you get 9 over x minus 3. Used your skills in limits. Factor the top as a difference of squares. And now we could plug in 3. And we got that it was equal to 6. So formula number 1 allowed us to find out the slope was equal to 6 for that specific point. Okay. Then we learned formula 2. Formula 2 was another formula for slopes. It was the limit. It was the same idea, but now it was h goes to 0 of f of a plus h minus f of a over h. And again, we had our function was x squared, and we're still using the point 3, 9. So formula 2, what it meant to do is saying, well, what's our a value? What point are we looking for? We're looking for when it's equal to 3. So we would plug this into our formula, and we would have equals the limit as h goes to 0. Well, 3 plus h squared minus 9 over h. And if you simplified this limit as h goes to 0, well, this would give you 9 plus 6h plus h squared minus 9 over h. Your 9s cancel out. You could factor out your h now. 6. And evaluate it to be 6. Same slope as before, which it should be. I'd hate to do the second formula and find out we got a different number. So once again, plugging in a specific point, and both formula 1 and formula 2, right, the a is a specific point that you're plugging in. We want to find it at 3, 9. So by plugging in 3 and simplifying, we get the correct slope at that point. Now, the definition of the derivative, which we just completed here, it says instead of plugging in a specific point, the difference now is you're plugging in a general point, any point x along there. And if we plug in a general point or any point and go through the same process, and you look at how similar the definition is to the actual formula 2, they're identical except one plugs in a value, the other one leaves your variable x. Right? Instead of 9 squareds canceling out, or 9s canceling out, we have x squareds canceling out. And when we evaluate our limit here, this is so much more powerful because now we have a formula for all the slopes. No matter where, as we drew here on the next slide, no matter where on our parabola we want to look at, we can find the slope of the tangent anywhere. I can find it at 3 just by plugging in 3, I get 6. But if I wanted to find it with -2 with formula 1 or formula 2, I'd have to do the whole process again with different numbers. The definition just says you do it once, you get your formula for all the slopes. And then you can find any slope at any point. And then you could find the equation of any of those tangent lines if you wanted to as well. So the definition becomes a more powerful way for us to find any slope of any tangent at any place. And what we're going to be developing in unit number 2 is a bunch of different derivative rules so that we can find them fast. But right now, the only tool that we have for finding the derivative is this definition. The limit as h goes to 0 of f of x plus h minus f of x. And again, this, just a reminder, this is really just rise over run. We made h the x value, the distance of the triangle and the x value, and f of x plus h minus f of x, your rise. So we're just using a formula for slope to figure it out. And so the idea itself is kind of a simple idea. I'm sorry, calculus isn't that complex. But it's amazing at what this all does as far as the power it can do to solve complicated questions later on. So let's look at one more example, a square root one. We want to find the derivative function if the original function was y equals 3 root x. So again, you're going to need to know Newton's quotient or the definition of the derivative. Rise over run. That formula you're going to need to know memorized, or if you can think about how we figured out the formula, where it comes from, that can help you memorize it. And in our example here, we're doing the limit as h goes to 0. The original function is 3 root x, so plugging in x plus h would be 3 root x plus h minus 3 root x all over h. What has been our main strategy whenever we have square roots? Multiply by the conjugate. So I'm going to multiply I'm going to multiply top and bottom by the same thing, except have a plus sign in between. That makes the top a difference of squares. Square this one minus square this one all over, and I'm not going to multiply out the bottom because I want to keep that that h factored out, because that's what I want to cancel. That's what I want to get rid of. Can you see on the top, if you have 9x plus 9h minus 9x, that you'll just be left with 9h in the numerator? And since that h stayed factored out, we can now simplify. And as soon as that h goes away, you now can ask yourself, could I plug in h without dividing by 0? The answer is yes. My numerator would be 9. My bottom would be 3 root x plus 3 root x, which would equal 6 root x. And so now I've got a formula for anywhere on 3 root x. Okay? Graphically, what does 3 root x look like? Right? That's a square root graph. that's been stretched by a factor of 3, so you would have 0, 0, 1, 3, 4, 6. There's our graph of 3 root x. If I was curious and I took a point on here, how nice of a point? Well, we can choose any of those points will be fairly nice. If I choose this point right there, 4, 6, and I drew a tangent, I can tell just by my formula, if I plug in 4 for x, square root of 4 is 2, 2 times 6 is 12, I'm going to get a slope of, and I won't simplify that even though I could, 9 over 12 is the slope of that line. I could have found that slope using my formula 1 or my formula 2 from before, but this is more powerful because I now have my derivative finds any slope. So if all of a sudden I decide, ooh, I'd also like to know what the slope is at this point. What's the slope of that tangent line when x is 1? Well, now I can plug in 1 here. I know that slope is 9 over 6. What happens when you plug in 0 into your derivative? You divide by 0, which isn't allowed. Can you see that you sort of have an issue at 0 in that, is there only one tangent that I could have just touch at that point, or could I sort of have a whole bunch of them at 0 sort of swing around? And so it doesn't exist. In order for a derivative or a slope or a tangent to exist, there should be only that one tangent. As soon as you get more than one possible tangent touching that point, your derivative won't exist.